converges to basically as n goes to infinity. So this is what that we like to do. So I'm saying that, okay, let's play with it. Take any epsilon positive. By the way, do you remember definition of the convergence and probability? Definition of convergence and probability is that for every epsilon positive, probability of xn minus x being bigger than epsilon goes to 0 as n goes to infinity. Okay, that's what is the definition. So choose an epsilon positive and think about this guy. Okay, so this fx of x minus epsilon. What would be this guy? This guy is telling us that this is same as probability x less than or equal to x minus epsilon. Actually, epsilon is a small number. Okay. When the x is less than or equal to x minus epsilon, what can I say about xn? You know, xn can be anything. Apparently now, at the moment, xn has nothing to do with x actually, except it converges in probability. So in other words, I can break it down. So in other words, how can I, okay, this is also a good point to reflect and think that this is same as probability that x is less than or equal to x minus epsilon and xn is less than or equal to x plus probability that x is less than or equal to x minus epsilon and xn bigger than x. Okay? So how this miracle happened? So if I take this as event A and if I take then I can, and this as event B actually, then I can say A is equal to the part of A that falls in B and the part of A that falls in B complement actually. Okay? So A can be written as, you know, A union B and A union B. Okay, A intersection B union A intersection B. You got that. Now here's the interesting thing. If you have this, then I can write this as, or maybe I can say this is less than or equal to probability of xn less than or equal to x plus this is same as the probability that xn minus x is bigger than epsilon. Who can explain this miracle?
Xn minus x.
So here's the thing. So this is A intersection B and this is B. So the A intersection B is part of B. So the probability of A intersection B must be less than or equal to the probability of B actually, for sure. Now with this I can show that any omega that satisfies these two inequalities must also satisfy this equality. Okay? You know, I mean, you can make a picture of it and think about it, or you can think about it. Okay. So if the x is less than or equal to x minus epsilon, and xn is bigger than x, okay? Can you see it? Shall I go in detail, or you can already see it? You can see it. Okay. So in other words, I can encapsulate. So the omegas which satisfy this must also satisfy this basically. Okay? So if you are happy of not getting into the argument, you can think about it, making it rigorous. But you can see one thing is that using these two inequalities, I can show that xn minus x is bigger than epsilon and xn minus x is less than minus epsilon. So in other words, these both inequalities can be proved using these two inequalities. So therefore, those omegas for which this is true, this must be true. So therefore, those omegas which satisfy this is a subset of the omegas which satisfy this actually. So therefore, the probability should be less than or equal to. ठीक है. Okay, are we? Shahrukh is not happy with it, huh?
Yes, sir, I am happy.
Already happy?
Yes, sir.
Good.
I can explain that if you want.
Okay, no, thank you. By the way, this would be what? This would be fxn of x, okay, plus the probability that xn minus x is bigger than epsilon. Agree? So what I'm saying is now take what? Lim soup on both sides. A limit from both sides. Can I take the limit on both sides? If I take limit from both sides, this is going to stay same. Okay? And this would be less than or equal to lim inf, okay, of fn of x. Basically, I'm directly writing the equation and see that whether you are happy with it or not. Lim inf of fn of x plus lim soup of probability of xn minus x being bigger than epsilon. Okay? ये तो आसान है. Okay, ये तो आसान है क्योंकि you have a sequence and you have a lim soup. Okay? So the only thing is this part actually. Okay? And in fact, if we see this is 0 actually. This guy is 0 because
P में
convergence है. So you have, so the lim soup would be equal to the limit actually, and that goes to 0 as n goes to infinity. So in fact, this is 0. Okay? The key thing is, can you see this? Who knows? Figure it out for yourself. Okay? So, with this equality, think about it. So what do you get? You get the lim inf fn of x as n goes to infinity. Okay, so this is something that we did. By the way, by a similar, so what ultimately we have shown, so fx evaluated at a, some, what do you call, a nearest point, a left hand point of x is less than or equal to what you call lim inf factor. And then I can also show, have a guess, what would be this factor? Okay.
Greater than suprema?
So it must be the greater than or equal to lim soup actually of fn of x. Okay, so you can show on the same lines. And what does this shows? That it shows what? Okay, it shows this, and if you have a continuity, in other words, if you take epsilon to 0, okay, I can take this epsilon to 0 on the left and the right because you have continuity. What you can show, in other words, if I take epsilon goes to 0 in both of these inequalities, this would be equal to fx of x and this would be equal to fx of x because x is the point of the continuity actually. Hence, I can deduce, so this fx of x is sitting between what? Interestingly, lim soup, okay, and less than or equal to infinity, fxn of x, and lim soup, and goes to infinity, lim inf Are we done?
Sandwich theorem.
What should I add in this inequality once more to get what we want? Do we need to add anything? So do you see anything unusual actually? So the lim soup is less than or equal to lim inf. Wow. Can we have it? Anyway, so I can say that this is less than or equal to lim soup of fx sum of x as n goes to infinity. There you go. The lim soup
Is equal to the lim
is lim inf and equal to fx of x, and we have a result which says that if you have lim soup and lim inf, then they are sharing a limit, then that's your limit actually. Okay? So this completes the proof. Okay?
That's deep.
Good exercise in basic analysis. So it's already 6, around 6. So what I'm going to do, this means that it's better that if you directly try to do the central limit theorem, I'll state a result, and maybe in the next discussion, okay, maybe as a seminar, I'll give you the proof of, or maybe in the stochastic analysis course, if some of you people are taking that course, I can give you that property of continuity. Because I'm just mentioning it. You know why I was interested in it? Because there were a hell lot of new things that you must have been exposed. For example, you will have known, okay, that what do we mean by a sequence of probability measure converging to another measure actually. So forget about random variables and forget about numbers. What do we mean by somehow sequence of probability measure converging to a measure? Okay, and what do we mean by a sequence of probability measure being tight actually. So you have a tightness property in probability theory as well. Okay? And it's the tightness property basically that allows you to prove what is called this continuity theorem that I'm mentioning. Okay. So basically I was thinking maybe that's a good opportunity to expose some of these notions. Okay. Don't have much time, so but if you get time, you can read. I mean, if you see what we are doing at the moment is really the end of the 5th chapter of this book actually. Because the first part of 5th chapter of book we've already done it, because it's all about modes of convergences actually. Okay, so what you are doing is basically trying to prove a result which is important for proving central limit theorem. So when you mention that result and then write central limit theorem in its precise statement and then prove it, you see that it's not that difficult. So the theorem says so let me mention a lemma. There are different versions of central limit theorem. So what we are proving is an elementary version. Obviously there are many generalizations of central limit theorem. Okay, but that's what the beginning is. So let me give a lemma. So I say that let Zn be a sequence of random variables. The sequence of random variables with law. By law, sometimes, this CDF is also called law actually. Okay, so, most particularly law, it's called law. Okay. The law that a, random variable is following, in other words, the law to distribute the probabilities. Okay. With law f(Zn), in other words, these are distribution functions. Okay. And Z be a random variable, okay, with law fz, distribution function fz. Okay. So what essentially this theorem is telling you, basically it's a kind of continuity properties. It tells you that if you take the moment generating functions are the characteristic function, it's true for both. If you take the moment generating functions of Zn and you prove that they converge to the moment generating function of Z actually, pointwise. Okay? Okay? Converge to in pointwise. Then, so if you have this, then Zn converges to Z in distribution. Okay, so it's a kind of a sufficient condition to prove that Zn converges in distribution to Z actually. So what you only need to show, so now if you want to show this, just show that the moment generating functions are converging basically. The moment generating function of sequence is converging. Okay? Does it make any sense? So let me write the central limit theorem. Now this is a result which requires a lot of analysis basically to be done. So it's not a one simple result. You have to do lots of, so it's lots and lots of basically mathematics actually to prove basically this is the and I was thinking maybe we can go through some of it, but it turns out that it's difficult, but I highly encourage you to read. It's a readable thing. Okay. I mean, if you have time, okay, after the exam we can set up a seminar, okay, and we can do these properties, but the basic things, for the basic things in any subject, in other words, you want to master a subject, try to learn as much as basic facts about that subject, because when you are doing advanced things there, okay, you're doing research, you're doing some kind of a project, so the writers and people write, for example, in paper, so they assume the people know the basic facts, so they're not going to explain the fundamentals to you. Okay, so and that's what sometimes makes paper, especially in analysis, make them difficult to read, because there are lots and lots of small things actually, okay, that you know sometimes and that you don't know sometimes. You all the time scratch your head how the heck this follows actually, but it follows from something very basic. Anyways, so what is CLT, central limit theorem? So as I said that if you take, so intuitively if you take lots and lots and lots of random quantities and you put them together, they're gonna create a blob actually. Okay? You see the truck of bricks is coming and people are taking out bricks and throwing them somewhere, so you're gonna get a blob actually, three-dimensional blob. So it's like central limit theorem, that you throw things, you collect things at one place randomly, it follows normal distribution. Okay, that's a miracle. You will see that why this miracle is so powerful. So here you have a sequence. Let this sequence be IID. Okay, and having mean mu and variance sigma square. Okay, then this guy, x1 plus x2 plus so on and so forth, xn, in other words,